Hello and welcome to our lesson on the ellipse. This is going to be from section 10.3 in our Precalculus text. First, we're going to cover this information sheet you see in front of you, going through all of the formulas, both vertical and horizontal major axes. Then we're going to jump over to Desmos and give a graphical representation of this content. And finally, we're going to look at some examples illustrating what you're going to need to know how to do when it comes to working with the ellipse. So let's get started. The first thing I want to draw your attention to is this relationship. And this says that a squared has to be bigger than b squared. And that is going to determine whether you have a vertical major axis or a horizontal major axis. So, just to break it down and make it as simple as possible, if the bigger number is under the x squared, you're going to have a horizontal major axis. If the bigger number is under the y squared, you're going to have a vertical major axis. And I would like you to notice that in order for your ellipse to be in standard form, the equation must be equal to 1. Next, the center of the ellipse is the same regardless of whether you have a vertical or horizontal major axis. The center in both cases is the ordered pair h, k. The vertices are going to depend on which major axis you have. So if you have a vertical major axis, your vertices are going to be h, k plus or minus a. For a horizontal major axis, the vertices will be h plus or minus a, k. And when it says vertices, these are referring to the major vertices. There are also minor vertices that we will discuss in the Desmos window. Next, the foci for a vertical major axis are going to be h, k plus or minus c. And for the horizontal major axis, the foci are h plus or minus c, k. So one other thing to note before we move on, sometimes they will give you the vertices and the foci, or the center and the vertices, or the center and the foci, and they will ask you which is the major axis. So I want you to notice that for the vertical major axis, all of the x-coordinates are h, which would indicate that if the x-coordinates are identical, you're going to have a vertical major axis. Likewise, for the horizontal major axis, notice that the y-coordinates are all k, and this would indicate that if your y-coordinates are the same, you're going to have a horizontal major axis. Next, the major axis equation is 2a. Now what that means, it means if you want to find the length of the major axis, all you need to do is multiply a times 2. That will give you the length of the major axis, and the minor axis equation is 2b. So if you multiply b by 2, you get the length of the minor axis. One more important concept before we move to Desmos is the Pythagorean relationship. So for an ellipse, this Pythagorean relationship holds true. A squared equals b squared plus c squared. And this is going to be very important if you know two of those variables and you need the third. Now, let's jump over to Desmos and look at a graphical representation of this content. So we're going to start with the ellipse with a horizontal major axis. I've got the equation input here. You're going to see that a horizontal major axis means that the ellipse is longer horizontally than it is vertically. I've got the center already turned on. Notice the center is the ordered pair h, k. Then looking at the foci, remember those were h plus or minus c, k. and you can see the location of the foci in the ellipse. Next, the major vertices on the ellipse would be the endpoints of the ellipse where it is the widest. Here we have the ordered pairs h plus or minus a comma k. And if we turn on the major axis, you're going to see that that is the length across the ellipse in the widest direction. And that length is 2a. And so here you can see that in this particular setup, we're going from -8 to 8. So the length of the major axis would be 16. Next, the minor vertices that we didn't mention in our information sheet. In this particular case, where you have a horizontal major axis, the ordered pairs are h, comma, k plus or minus b. And you can see those vertices are the endpoints going across the short direction. The minor axis will stretch across and have a length of 2b. So in this case, we're going from -4 to 4, so the distance across there would be 8. And the next thing I'd like to discuss is what is special about an ellipse. So what I've drawn here is a line from the focus to a point on an ellipse, and then a line from that same point to the other focus. What is special about an ellipse is no matter where the point is on the ellipse, the sum of the distances of these orange lines is a constant. And I've got that right here. The distance 1 plus distance 2 would be the distance of the first orange line, and then the distance of the second orange line added together gives me their total distance. And I'm going to swing that around the ellipse. You're going to see that the distances are changing. The distance for line 1 and line 2 are changing, but the total is not. So that sum is always a constant. Now, another cool thing that might be nice to know is that the length of the major axis will always be that total distance. Might want to make a note of that. Whatever the length of the major axis, that will also be the total distance, which is the sum of these two lengths of the orange lines. And there is one other cool feature about an ellipse here that I'd like to explain. There are these things called whisper rooms, where there's spots on the floor marked to represent the two foci. And if a person stands at one focus and another person stands at the other focus, no matter how far apart they are, the person at focus 2, if he even so much as whispers, the person at focus 1 can hear him, and nobody else in the room will hear what the person said. Now, why is that? That's because if you're standing at focus 2 and you say something, all of those sound waves are going to hit this point on the ceiling, which would be represented by an elliptical curvature. And no matter which direction the sound wave goes, it's going to be redirected back to the focus. So all of those sound waves emanating from this focus 2, even if it's behind, when it hits the ceiling of the whisper room, it's going to be redirected to the other focus. That is freaking cool in my opinion. Now, let's briefly discuss how these variables in the ellipse will alter the position and the curvature of the ellipse. So h is attached to the x. So if I change the value of h, notice that that is going to shift the ellipse left or right, depending on whether h is negative or positive. The value of k is attached to the y, so that will shift the ellipse up or down, again, depending on whether k is negative or positive. The value of a is going to adjust the length of the major axis, making it shorter or longer. And if we bring that all the way in so that the foci are at the center, I want you to notice that that does make a circle. So a circle is a special kind of ellipse where the foci are also at the center. And the value for B is going to change the length of the minor axis. Did you notice that as the length of the major and minor axis change, it also shifts the foci, which is kind of cool. And again, we have our special note that A must be bigger than B. Both of those must be positive. And let's briefly run through the vertical major axis ellipse. Again, here you can see I have the formula for an ellipse with a vertical major axis where the big number is under the y squared. I have all the same variables and sliders, and they're going to do the same thing. So H is going to shift the graph left or right. K is going to shift the graph up or down. A is going to stretch or shrink the major axis, and B will stretch or shrink the minor axis. The center is still H, K. The foci now have to lie along the vertical axis, and those formulas are H, K plus or minus C. The major vertices, again, are the vertices in the longest direction. In this case, H, K plus or minus A. The minor vertices, in this case, H plus or minus B, K, lie along the minor axis. And again, I want to illustrate what makes an ellipse special is that the distance from the focus to a point on the ellipse plus the distance from that point to the other focus will always be a constant. Notice as I'm moving that point around, the two lengths change, but their sum does not. And remember I said that that total distance will be the length of the major axis. So if I adjust that A value to 5, remember the length of the major axis is 2 times A, and so this sum should be 10, and it is. And that's going to do it for our Desmos overview of the ellipse. Now let's go look at some examples. So in the examples we're going to look at, there are two forms of an ellipse. There is standard form and there is general form. Now these formulas that we referred to back in our ellipse information sheet, these are standard form where your equation has to equal to 1. General form will have the equation equal to 0. So you won't have any parentheses, no grouping symbols, and the equation will be equal to 0. Of course, if you have two different forms, one of the things you may be asked to do is to convert back and forth between the two forms. One of the other things you may be asked to do is, given one of these two forms, you may be asked to find the critical information, like the center, the vertices, the foci. Any of this information you could be asked to find if you're given the equation of an ellipse. Likewise, if you're given the center, the vertices, the foci, the constant distance, a point on the graph, the length of the major or minor axis, and it would require a combination of these in order to find the equation of the ellipse. So for example, you can't just be given the center and expect to find the equation of the ellipse. You have to be given enough information so that you can find the key variables, which are H and K and A and B, in order for you to establish the equation of the ellipse. For our first example, we're going to be given the equation 4x squared plus 9y squared equals 36. And what we're going to do is we're going to convert this into standard form and then find every possible piece of information we could find. So to start with, I really need this 36 here to be a 1, and the way I can get that is dividing by 36. But whatever I do to one side, I have to do to the other. So we are going to divide everybody by 36, and then I need to reduce. So 4 will go into 36 9 times. That will give me x squared over 9. Plus 9 goes into 36 4 times, giving me y squared over 4 equal to 1. And then I'm going to put a box around this because this is my standard form of the equation of the ellipse. And remember that I said that the big number in the denominator is a squared. So we're going to make a note of a couple of things here. A squared is 9. B squared is 4. Also, in order for the numerator to only be x, that would indicate that h must be 0. And for the other numerator to be only y squared would indicate that k must be 0. And so there's 4 pieces of the puzzle that I now have, and now I can find some stuff. Let's start with the center. The center is super easy. That is the ordered pair h comma k, which in this case would be the origin. Next, the major vertices. Knowing that x has the biggest denominator, that indicates that we're using this formula, and then these formulas apply. So the major vertices are going to be h plus or minus a comma k, and then once I have the correct formula, I just need to plug and play. H is 0. Now a, we would need to take the square root of both sides to find a to be 3. So that's going to be 3 comma k, which is 0. And then that gives me major vertices of negative 3 comma 0 and 3 comma 0. Next, the minor vertices, well, in this case, would be h comma k plus or minus b. And then doing a little plug and play here, h is 0, k is 0, b, we're going to need to take the square root of both sides, b is 2, and then I need to replace b with 2. And so my minor vertices are going to be the ordered pairs 0, negative 2, and 0, 2. And let's put a box around those. And at this point, I do have enough information to sketch the graph. Once you have the major and minor vertices, you can get a good picture of the graph. So the major vertices, 1, 2, 3, at negative 3 and 3, and the minor vertices at 2 and negative 2. And then we just need to connect the dots and make it look something like an ellipse. Something like that. Now, remember the center was at the origin. The foci are going to have to be somewhere along the major axis. So taking our Pythagorean relationship, we're going to replace a squared with 9. We're going to replace b squared with 4. And we're going to solve for c. Subtracting 4 from both sides, 9 minus 4 is 5. That's going to give me c squared. And then we're going to have to take the square root of both sides. So notice that c is going to be the square root of 5. So the formulas for the foci, since they have to lie along the major axis, that's going to be h plus or minus c comma k, which would be 0 plus or minus the square root of 5 comma 0. And then to write those as separate ordered pairs would be negative square root of 5 comma 0 and square root of 5 comma 0. And then if I wanted to estimate where to plot those, I would need to, well, estimate the square root of 5. Luckily, we have our calculator handy. We're going to estimate the square root of 5 to the nearest tenth, and that would be 2.2. Approximately 2.2 left and right of the origin. So 2.2 is going to be about here and here. Those would be the foci. And recall that if you measure the distance from one of the foci to a point on the ellipse, and then measure the distance from that point to the other foci and add those together, that is going to be a constant. Now, do you remember what that constant is? Recall that that is twice a. Or, in other words, that is the length of the major axis. So, a was 3, so we know that that constant distance would be 2 times 3, or 6. And so at this point, I have found pretty much everything you could want to find, including the length of the major axis, which is 6. Oh, and I guess the other thing I might want to find is the length of the minor axis. Remember, that is 2b, and b was 2. So the length of the minor axis would be 4. Well, we can see that if you take a look at our graph and we measure across the short way, that is a distance of 4. So that is the length of the minor axis, and the length of the major axis, if we measure across the long way, that would give us a 6. And so that's one way you can visually check to make sure you've calculated those correct values. And that's going to do it for our first example. For our next example, we are given the equation of an ellipse in standard form. And let me briefly explain what you would do if you needed to convert to general form. I can't imagine that you would ever want to go that direction, but if you did, the first thing you would have to do is multiply both sides by the common denominator so that you could clear the fractions. And then you would need to FOIL both of the numerators here. Once you get rid of the fractions and the parentheses, you would move everybody over to the left so that you could set that equation equal to 0. And so that is the process that you would go through to go from standard form into general form. What we're going to do is we're going to take this information, this equation, and we're going to find pretty much everything you could want to find for the ellipse. Starting out, the formula in this case would be x minus h. So we know that minus h would be 4. Y minus k, we can see that minus k would be 2. And a squared, remember that is the bigger of the denominators, and b squared is the smaller of the denominators. So, making a list of what we have, we know that negative h is 4. Changing the signs on both sides would give us h is negative 4. We can also see that negative k is negative 2. Changing the signs on both sides would indicate that k is positive 2. And with these two pieces of information, we can get the center, which is the ordered pair h comma k. Now, we can also see that if a squared is 9, taking the square root of both sides would give us a is 3. And if b squared is 4, taking the square root of both sides would give us that b is 2. If I know A and B, I can find C. Using our Pythagorean relationship, A squared equals B squared plus C squared, we're going to replace A squared with 9, B squared with 4, and we're going to solve for C squared. So, minus 4 from both sides. 9 minus 4 is 5. And then if I take the square root of both sides, I have my value for C. And since it doesn't square root nicely, we're going to leave that in simplest radical form. So now that I have A, B, and C, I can find the major vertices. Again, remember that A squared has to be bigger than B squared. So the biggest denominator under the x squared indicates that we have a horizontal major axis and indicates that we're going to be using these formulas again. So the vertices, the major vertices, h plus or minus a comma k. The minor vertices would be h comma k plus or minus b. And the foci, h plus or minus c comma k. All right, here we go again. Plugging in for h. H was negative 4 plus or minus a was 3 and k was 2. And then I want to simplify those into the two separate ordered pairs. So we're going to do the plus first. Negative 4 plus 3 is negative 1, comma 2. And then we're going to do the minus. Negative 4 minus 3 is negative 7, comma 2. And I've got my major vertices. And next, the minor vertices we said would be h comma k plus or minus b. And so again, doing a little plug and play, h negative 4, k was 2, plus or minus b was also 2. And then writing those as our two separate ordered pairs would give us negative 4. 2 plus 2 is 4. And we're also going to have negative 4. 2 minus 2 is 0. And if you're wondering how to determine, do you see I'm using m vertices for both, but I'm using a capital M and then a lowercase m. I don't know if you can tell that or not, but that's how I designate major vertices versus minor vertices, capital or lowercase. Remember we said once we get the vertices, we can get the graph. So let's go ahead and sketch a quick graph of this ellipse. So the major vertices would be at negative 1, 2, and at negative 7, 2. The minor vertices at negative 4, 4, and at negative 4, 0. And then we're going to connect the dots and make it look sort of like an ellipse. There we go. Not very good at the hand-drawn ellipse, but you get the idea. Again, we can check the center if we want. The center should have been at negative 4, 2, which looks like the center. And if you recall from our previous example, we approximated the square root of 5 to 2.2. And so we can see that the foci are going to have to lie along the major axis. And so that would indicate that the formula for the foci are going to have to be h plus or minus c, comma k, which would be negative 4 plus or minus the square root of 5, comma 2. And then you're going to need to approximate those. That is about 2.2 away from the center in both directions. So that should give us our foci. The length of the major axis is 2a. So that length would be 2 times 3, which is 6. The length of the minor axis is 2b, which would be 2 times 2, which is 4. And don't forget that the length of the major axis is also the constant sum from the distances to a point on the graph to the foci. And that should do it for the second example. For our third example, if you've been wondering what an ellipse looks like in general form, this is it. This is the equation of an ellipse given in general form, where we don't have any grouping symbols. There's no fractions, but there could be. But it does have to be equal to 0. And so our goal, in order to find some information about the ellipse, like the vertices and the foci, we're going to need to convert this into standard form so that we can find the values of h and k and a and b, and then we'll be good to go. So the first step to convert into standard form would be to group our x's together. So we have x squared plus 6x, and then in order to get that into a set of parentheses, in order to factor that, we're going to need to complete the square. So I'm going to put plus a blank where we're going to come up with the constant that gives us a perfect square trinomials. And then we're going to go for the y's, grouping our y's together. Again, in order to get this factored, we are going to have to complete the square. So again, I'm going to put plus a blank in order to complete the square. And if they do give us a constant, you're going to have to go ahead and move that over. And then don't forget that we're going to have to add to both sides whatever we added to complete the square. And now we're going to complete the square. For the x's, we need to divide by 2. Half of 6 is 3. 3 squared is 9. And that completes the square, putting the 9 on both sides. Oh, and if you want to go ahead and hack and slash, you can do that. Those 9s are going to cancel. But for the y's, notice that we do have a lead coefficient, and we're going to have to factor that out. In order to complete the square, the coefficient of the y squared has to be 1. So watch carefully. I'm going to factor that 9 out, which would then make, instead of 18, that would become a 2, right? If I distribute the 9, I have to get the 18 back, so that would give me a 2. And then I'm going to close the parentheses, and now we're going to complete the square. Taking half of the coefficient of y, half of negative 2 is negative 1. Negative 1 squared is 1. And remember, whatever I add to one side, I have to add to the other. So we're going to add 9. Hold on. Wait a minute. Do you understand why that's a 9? Notice that 1 is inside the parentheses, and so the 9 would distribute to it also. So what I added was not really a 1. I really added a 9. And so that's why I have to add 9 on the other side. Please be careful about that when you're completing the square and you had to factor out. And now we need to factor. So for our first perfect square trinomial, that's going to factor as x plus 3 quantity squared plus 9 times y minus 1 quantity squared equals, and all we have on the other side is 9. And then remember, to get to standard form, the constant over here needs to be 1. And so we're going to have to divide everybody by 9. And to simplify, these 9s will cancel, these will cancel, but remember, canceling means you're dividing. Anything divided by itself is 1. And so our standard form is going to simplify to x plus 3 quantity squared over 9 plus y minus 1 quantity squared. I'm going to go ahead and write over 1 so that we can see the value of b squared equals to 1. And let's put a box around that because we're done. This is now standard form. And now I can find h. H is always opposite of what's with x. Opposite of plus 3 is minus 3. K is always opposite of what is with y. So k is going to be opposite of negative 1, which is 1. A squared, remember, is the bigger of the two denominators, and b squared is the smaller of the two denominators. And do you understand at this point, once I get to standard form, I'm just gathering information, and then I can find whatever they ask me to find. For example, we can get the center now. That is super easy because the center is h comma k. The foci I can't get yet because I don't have the value for c, but I can get the major vertices. Remember, since the bigger number is under the x squared, that's going to indicate that we once again have a horizontal major axis, and then we're using the second column formulas. So our major vertices would be h plus or minus a comma k, which would give us negative 3 plus or minus a. Whoops, going to have to take the square root to get that a is 3 comma k. And then you do need to separate those into the individual ordered pairs. So here our major vertices would be negative 3 plus 3, which would be 0 and 1. And then negative 3 minus 3, which would be negative 6 and 1, giving us our major vertices. Our minor vertices, in this case, would be h comma k plus or minus b, which would be h, negative 3, k is 1, plus or minus, gonna have to square root, well, b is 1. And then writing those as the ordered pairs, we would have negative 3 comma 1 plus 1 is 2, and negative 3 comma 1 minus 1 is 0. Those are our minor vertices. And now let's go ahead and find the value of c. Now, since it occurs to me that we're having a and b a lot and we're having to solve for c, you might want to consider rewriting this Pythagorean relationship so that c squared is by itself, or even solve for c. So if we subtract b squared from both sides, this Pythagorean relationship becomes c squared equals a squared minus b squared. And then if you take the square root of both sides, you can get the value for c. So this would be another equation that you could use if you are given a and b a lot and you're just looking for c. So let's see if we can make that work. So c would be the square root of a squared minus b squared, which would be the square root of a squared, remember, was 9, minus b squared was 1. 9 minus 1 is 8, and that can simplify. So to write that in simplest radical form, we would rewrite 8 as 4 times 2, and we can take the square root of 4, and this 2 is left underneath. So from there we can get the value of c is 2 square root of 2, and then I can find the foci. So the foci have to lie along the major axis, and this is our major vertices. So our foci would have to be h plus or minus c comma k, which would be negative 3 plus or minus 2 square root of 2 comma 1. And then if you wanted to write those as the two separate foci, you could by separating that into the plus and minus x coordinates. And just for fun, let's get the length of the major axis. Remember, that was 2a. A in our case was 3. So 2 times 3 is 6. The length of the major axis would be 6. And the length of the minor axis is 2b, which in our case, b was 1. And so the length of the minor axis would be 2. And you could sketch a graph of this if you wanted to. I'm not going to take the time to do that. And that's going to complete our third example. For example number 4, now we're going to flip the script where we're given some information about the ellipse and they want us to write the equation. So here we're given that the center is at the origin. We are given only one of the foci, which would be a focus, and we are given only one of the vertices. Now, if they designate an ordered pair as a vertice and they don't indicate whether it's a major or a minor, it's going to be a major, okay? So this is going to be one of our major vertices. With this information, I would like to draw your attention to the x-coordinates. Did you notice that all of the x-coordinates are identical? So going back to our information sheet, I think I alluded to this earlier, that if all of your x-coordinates are identical, then you're going to have a vertical major axis, and this is the standard form of the equation that we're going to be shooting for, okay? All of these formulas apply, and this is where we're headed. So the center is easy. Remember, the center is h comma k, and from that we can get the values of h and k. But notice that the foci has a negative y-coordinate and the vertex has a positive y-coordinate. So what I want to do is come over here to the side and just sketch a quick graph. I want to plot the vertex at 0, 5, but then I want to plot the focus at 0, negative 4. And remember, we said that this is going to be a vertical major axis, and if we're centered at the origin, then the other vertex is going to have to be equidistant from the origin. So this vertex was 5 units up, so the other vertex is going to have to be 5 units down. And so from this we can get the value of A. And from the focus, knowing that the ordered pair they gave me is at 0, negative 4, the foci are going to have to be symmetric around the origin. So our other focus is going to have to be at 0 and 4. Remember that we said that the formula for the foci were going to be h comma k plus or minus c. And since this y-coordinate is negative, that indicates that this coordinate came from the k minus c. Also for the vertex, that is h comma k plus or minus a. And since this coordinate is positive, then that came from the k plus a formula. We know that k minus c has to be negative 4, and k plus a has to be 5, but we know that k is 0. So we can eliminate those k's, and look what we have. We have a is 5, and if I change the signs on both sides, I now have c is 4. Once you know a and c, you can get b. So back to our Pythagorean identity. A squared equals b squared plus c squared. So a squared is going to be 5 squared, which is 25. B, we don't know, so that's going to stay b squared. And c squared is going to be 4 squared, which is 16. And solve for b. So we're going to minus 16. 25 minus 16 is 9. Gives us b squared. And then if you're wanting to take the square root, please resist the urge. Remember, when we're writing the equation, we need b squared, not b. I now know a squared and b squared. I know h and k. I can now write the formula. Starting with the standard form equation that we have in our information sheet and doing a little plug and play. If h is 0, x minus 0 is just x squared over b squared, which we know is 9, plus if k is 0, y minus 0 is just y squared over a squared, which is 25, and that's going to equal to 1, and that's going to do it for this example. Next example. Here we are given some information about the ellipse, and they want us to write the equation. Now, lowercase f would indicate the foci, so here they have given me the foci. And they have also given me the length of the major axis to be 8. So right off the bat, remember the length of the major axis is represented by 2a, but that length is 8. And so we can find a immediately. The value of a is 4. Now, from the foci, I would like you to notice that the y coordinates are identical. So if we go back to the information chart, looking at the foci, where the y is unaffected. Do you see that here? Y is just k. So regardless of what the x coordinate is, the y coordinate has to be the same, which would indicate that we do have a horizontal major axis, and then that would indicate that all of these formulas, including our standard form equation, apply in this problem. So knowing that our foci formulas are h plus or minus c comma k, we can conclude that k is definitely 1, right? K is 1 because we have the same y coordinate, but we can also conclude that h plus c would have to be the larger of the two x coordinates. So h plus c would have to be 5, and then h minus c would be the smaller of the two x coordinates. And now we're going to use our knowledge of systems of linear equations, and we're going to be able to solve for h and c using the addition method. Adding, we're going to get 2h, the c's cancel, 5 minus 1 is 4, and then all of a sudden we know the value of h. In this problem, h is 2. Remember, we already said that k is 1, and if you know h and k, you know the center. And so let's go ahead and write that down. Even though they may not ask for it, I'm going to write the center is h comma k. Okay, back to business. Remember, if I know h, I can come back up to this equation, replace h with what it is, and then I can solve for c. So h is 2 plus c is 5, and I think everybody would agree that 2 plus 3 is 5, and so that gives me c is 3. If I know a and c, I can get b. So next, we want to use our Pythagorean relationship. A squared equals b squared plus c squared. A squared would be 4 squared, which is 16. B, I don't know, that's going to stay b squared. And c squared would be 3 squared, which is 9. Subtract 9 from both sides. 16 minus 9 is 7. And so now we have b squared. And again, if you're tempted to take the square root of both sides, please resist the temptation, because we really need b squared, not b. And now I believe we have all of the information needed in order to write the standard form of our equation. And taking the standard form of the equation of our ellipse and doing a little plug and play. We're going to have x minus h. Recall that h was 2, so that'll be x minus 2, quantity squared, over a squared. And a squared was 16, plus y minus k squared. Recall that k was 1, So that's going to be y minus 1 squared over b squared, which was 7, equals 1, and we're done. That is the standard form of the equation of our ellipse. And for our last example in this lesson, here we are given the center, a focus, and a generic point on the ellipse. And we need to find the equation. So where do you start with this information? Well, I need you to notice that the y-coordinates of the focus and the center are identical. And going back to our information sheet, if the y-coordinates for the center and a focus, well, in a vertex for that matter, if the y-coordinates are identical, then that indicates that we will have a horizontal major axis. So this is our standard form we're going to be shooting for. All of these formulas here apply to this problem. Now, if we go back to our information, notice I have written my formulas here underneath the center and focus, and I have written down our standard form. Let's do a little information gathering. Here we can see that h is 1 and k is 2. And so if I want to come over here to my formula, I can now replace h with 1 and I can replace k with 2. And do you see how we're moving along? We're making progress, moving towards getting all of the information needed so that we have our equation. So the two pieces that I still need to find are a squared and b squared. And focusing on the focus, we need to determine if this x-coordinate is going to be the h plus c or is it going to be the h minus c. And one way we can determine that is by sketching a little graph, knowing that we have a horizontal major axis. I'm going to plot the center, 1, 2, and then I'm going to plot the focus, which is at 4, 2. Now remember that the ellipse, well, it has to be centered on the center, and if it has a horizontal major axis, then it's going to do something like this. It's going to have to enclose the center and focus. Notice what that indicates is that since the focus that they gave me is to the right of the center, then that would indicate that it is the larger of the two x-coordinates, which indicates that that is going to be the h plus c coordinate. And now we can set up the equation h plus c equals 4 and solve for c. We know that h is 1, so 1 plus c has to be 4. And I think everybody would agree that 1 plus 3 is 4, and so c has to be 3. All right, so remember we need a squared and b squared, and just knowing c, that's not going to be enough information to use our Pythagorean relationship in order to calculate a and b. And so it may feel like you've reached an impasse, like you don't have enough information, but remember that they did give me this other generic point on the graph. And so what I can do is I can say, well, if x is 1 and y is 3, and that is a point on the graph, then I should be able to take this standard form and replace x with 1 and replace y with 3. But you see, I still have two variables in this single equation, and then this is where we're going to pull in our c in conjunction with our Pythagorean identity, and just watch the magic happen, okay? So our Pythagorean relationship is a squared equals b squared plus c squared. But I know c is 3, and 3 squared is 9, and now look what I've got. I now have a value for a squared that I can substitute in my equation, and I will only have a b variable, and then I can solve for b. So here we go. We've got 1 minus 1, which is 0. 0 squared is 0. And I don't know if you realize this, but 0 divided by anything is 0. And so I can completely ignore this first fraction. So in the other fraction, I'm going to have 3 minus 2, which is 1. 1 squared is 1 over b squared equals 1. And then if I multiply both sides by b squared, I'm going to eliminate my fraction. That's going to give me b squared is 1. And now that I know b squared, I can come back and find a squared. A squared would then be b squared, which is 1, plus 9, giving me a squared is 10. And now I can write the equation of my ellipse in standard form. That was x minus 1 squared over a squared, which is 10, plus y minus 2 squared over b squared, which was 1, equals 1. And that gets our equation, and that completes this example, and that's going to complete this lesson. So if you have any questions or comments about anything that I've covered in this video, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.